Okay, continuing with our discussion about BJTs or transistors, let's look at the physical construction. Okay, we saw the two-dimensional side view and the top view images. This is now a three-dimensional structure. Again, the dimensions are exaggerated, but it is quite evident what we are trying to show here. Okay, side view right here. We have the large collector, largest structure in here. We have the base created inside the collector, but it is very, very thin, which is not apparent in either one of these images, right? Then we have the emitter, the heavily doped emitter created inside the base. Okay, I want to point out, when we actually fabricate these, we start either with a P or an N-type material. So in this case, what kind of transistor are we trying to show? It says right there in the name. It's an NPN. So the collector is from an N-type material. Now, if it's an N-type material, it is not very heavily doped. Okay, it is not very heavily doped. It's somewhere between the emitter and the base. As I pointed out in one of the previous slides, collector is the largest physical in terms of physical dimensions, but in terms of doping, it is somewhere between the emitter and the base, right? And so what we show here is either, sorry, not P, N-type material for the collector. And so it shows it as N plus. N plus is simply in relation to the doping levels in that transistor. Okay, so we have the collector, the base, and the emitter, and it's just showing as N, or you could show it as N plus. The base is very lightly doped, so just P, and then the emitter is N plus. Compared to the collector, I would say it would be N plus or N plus plus. Okay, N plus or N plus plus. It's simply just showing you the varying levels of doping. Just means it's very, very heavily doped. That's all it's showing. Okay, and then the rectangular pads that you see on top, right, these are simply contact pads. Okay, contact pads. In the clean room class, we don't make transistors. We do make diodes, though. Okay, there is a separate mask process for transistors. It just gets too complicated. We can't fit it within 10 weeks. Perhaps when we get to semesters. All right. So this is also known as solid state devices. All semiconductor devices are known as solid state devices because unlike vacuum tubes, there is no actually moving beams. There is, of course, electrons and particles that are moving and flowing, but we can't see them. Right. So when they first created these devices, they came to be known as solid state devices. And so solid state electronics. All right. So essentially, they are two back-to-back diodes, but they do not function like two back-to-back diodes. And I explained in the previous, on Monday, how the function works, but we'll look at it in detail today with some images and some figures. Okay. Just want to talk about notations. The notations that we give for these terminals. So these are known as terminal currents. Is IB, IC, and IE. So base current, collector current, I, and emitter current, IE. And as you can see, the direction of the currents, base and collector flowing in, emitter coming out. Okay. And then we have the voltages, VBE, VCE, and slightly less VBC, which is not something that we are be really interested in. But terminal voltages VB, VC, and VE. The biasing voltages VBE and VCE. Okay. So depending on the applied voltages, we can have several different modes of operation. Okay. So the external biasing circuit will determine how our transistor is going to operate. Okay. So it depends on the applied VCC voltages and the applied VBB or the base voltages. Okay. VCC is typically applied between collector and emitter. And then VBB is applied typically between base and emitter if it is operated in the common emitter configuration. How many of you are done with lab 7? Interesting. Lab is way ahead of the lecture. You had what? Lab 7 is BJTs. So already done? Did you all use sweep and go? Okay, great. So the circuit is configured correctly. That takes less than 10 minutes. All right, so here's in terms of symbol. You have VCE, VBC, and VBE. You have IC, IE, and IB. Essentially, what is happening is you're applying a voltage between the collector and emitter, right? As I said, VCC, applying between emitter and collector. And so current should be flowing from the collector to the emitter or between the collector and emitter. And then you have IB that controls the flow of current. So you have a third terminal in there that you're applying at the base, and it controls the flow of current between the collector and emitter. Okay. As the base current increases, the collector current, what do you think happens? Increases. If it decreases, then it decreases. So IE, the total emitter current, is IC plus IB. The relationship between the collector current and the base current is known as beta. It is one of the most important parameters for a BJT. Okay. Just another illustration of how it works. We have IB and IC coming together to give us IE. Okay. And we'll talk about the equations in just a little bit. All right. So now let's look at that operation again. Okay. We have an NPN transistor. In the NPN transistor, we are biasing the emitter and base junction in forward bias. Okay. Again, this is NPN. The operation remains the exact same for PNP, except holes and electrons are interchanged. So all of the action begins in the emitter. The emitter is very heavily doped. It has a plethora of electrons, right? Huge numbers of free charge carriers. In an NPN transistor, it's electrons. In a PNP transistor, it's holes. All right. We forward bias this junction. Once we forward bias that junction, the electrons cross over into the base. This is what I was talking about last class, right? Electrons cross over into the base. In a PNP, the holes cross over into the base area. Now, the magic happens here is that the base is very lightly doped compared to the emitter and the collector. So when the electrons come in, recombination occurs, meaning the electrons will jump into the empty spots that they define. So electrons and holes will recombine, give off excess energy, and an electron hole pair disappears. But there are plenty of electrons and not enough holes to go around. And so, and that is, of course, on purpose, the base is very lightly doped, right? So there are all of these electrons just hanging around in the base, right, with nothing to do. Now, because the electrons and holes recombine, and there are holes that are going over here, so a small number of holes will cross over, right? It's a forward bias junction. But because the number of holes is less, the base current is going to be very, very small. There's just not enough number of free charge carriers. So IB is typically very small. Typically in microamps, right? Just tens of microamps. That's all. Even in the lab, when you simulate this, we're applying a base current of 10 microamps, 20 microamps, 30 microamps. So very, very small, right? Typically in microamps. And again, that's a result of the doping. All right, so now from chapter 2 and chapter 3. In an N-type semiconductor, holes are the minority carriers. Electrons are the minority carriers in a P-type semiconductor. So when you have electrons coming into the base, they are minority carriers, okay? Now, if you take the collector and the base junction, which is this PN junction. If you forward bias it, what would happen? You again, forward bias junction, you'd expect some current to flow through, but not enough because electrons are now going in the opposite direction. There are holes that are moving in there, just standard operation, okay? Nothing else results. But now if you reverse bias it, what do you think will happen? If we reverse bias it, the electrons, which are minority carriers in here, are able to cross the junction. Remember, again, if you recall from chapter 2. In chapter 2, we spoke about forward biasing and reverse biasing the PN junction. If you reverse bias a junction, the majority carriers are pulled away from the junction. So the depletion region keeps on expanding. But there's a small amount of reverse current that flows through because of the minority carriers that are crossing the junction. In this case, it's the exact same effect. The only difference is the minority carriers, which are electrons, are not from the P-type material, but they have come over from the emitter. They're hanging around with nothing to do, but because they're reverse bias, they're able to cross over and go into the collector region. And thus, current starts flowing because once they cross over into the collector region, they're attracted by the positive side of that applied biasing voltage. So all of those electrons cross over here, and now current starts flowing. Electrons flowing from left to right, current flowing from right to left. Hence, current enters the collector, base current enters into the transistor, and then flows out the emitter. That is the operating principle of a BJT. Let's take a pause, think over that. Let me know if you have any questions. So the question being asked is, why are we biasing in this way? And the answer is, well, in the question that we have, if we forward bias this, yes, there will current be flowing through, and we look at both modes of operation when both are forward bias. But essentially, yes, if we do not want to use them just as two back-to-back diodes, and we reverse bias the second PN junction, then yes, we can control the flow of current that is actually flowing through there. So the answer is all about control. How can we control the output current? In a diode, we have an external voltage. You apply that external voltage, and that's it. You don't have any other control other than the input voltage that's coming in. But if we wish to control, then we use forward and reverse bias mode of operation. Okay, so let me write that down here. This is forward bias. This is reverse bias. Okay. IB is typically very small. So for all intents and purposes, I can write IE is approximately equal to IC, or I should say IC is approximately equal to IE. Because we're talking about milliamps versus microamps, there's a factor of hundreds, okay, if not 1,000. All right, other questions? If you're online, feel free to interrupt and speak up. Just be aware there are speakers here in the classroom. But other than that, I would not be able to monitor the chat window. Other questions? Okay. All right. Based on the relationship between the three currents, we can describe the ratio of these currents as beta as alpha. So the ratio of collector current to the base current, which is the most important, is described by the Greek letter beta. So it's IC over IB. Sometimes it's also described as the current gain. And then the ratio of collector current to the emitter current, IE, is alpha. And since IC is very nearly equal to IE, value for alpha is typically around 0.99. And these are ratios of current, meaning they're dimensionless, no units. If you want to convert from beta to alpha, somebody on chat, please, somebody on Zoom, please send a chat and a message in the chat window. If you wish to convert from beta to alpha and alpha to beta, we use this equation, and also the other equation is alpha is equal to beta over 1 plus beta, if I remember correctly. Beta. Okay. Yes. No units. They're ratios of currents, so dimensionless, no units. Okay. Let's see. All right, transport model. So there are some equations that are in a book. I'm not going to rehash or repeat everything, but here, the transport model, what we are describing is we are applying voltages, we are applying biasing voltages, right? So there is a voltage drop that occurs between the base and the emitter. What do you think is the value for that voltage drop? What do you think VBE should be? Yes. I'm old, my ears are not that good. 0.6 to 0.7. Absolutely. So VB will always be approximately 0.6 to 0.7 volts. Lots of listening to loud music when I was your age, and even now on occasion. All right, so VBE would typically be 0.6 to 0.7 volts. It's a forward bias PN junction, right? VCE and VBC depend on the biasing conditions. So the voltage between the base and the collector and the voltage between the collector and the emitter depend on the mode of operation of the transistor. Okay, VCE can be anywhere from 0.2 to 0.3 volts to, well, 5, 6, 7, 8, 9, 10 volts, depending on the applied biasing voltages. All right. So again, we can model this in the the transport model. We can have two diodes. We are modeling this by applying voltage source VBC and VBE between the three terminals. Okay. Terminal currents are IC, IB, and IE. Terminal voltages VB, VC, and VE. One difference between the FET and the BJT is that for an FET, the gate current is equal to 0. In a BJT, the base, which is the controlling terminal, will require a certain amount of current for it to actually operate or turn on. Okay. For MOSFETs, it's again the same thing. We learned about MOSFETs in the last week, but for MOSFETs, the gate current is again 0. There is no current going into the gate. We are simply applying a voltage in order to create the channel, and that's it. And that's also one of the reasons why MOSFET devices are preferred, because it doesn't require any current at the base to actually turn it on. Okay, let's see. All right, forward characteristics using this transport model, right? We have, if we simply take this forward bias junction and we say VBC is equal to 0 volts, right? We are measuring the current going in one direction, which is here, forward current. And so this is known as the forward transport current. Forward transport current. And in this case, I'm saying the collector current is my forward current. IC is equal to IF. Okay. Now these equations are there in the book, and it's based directly off of the, well, I'll let you tell me what it's based on. It's a PN junction, and so familiar? Based on the diode equation. Okay. IC or IF, forward current, saturation current, E raised to VBE over VT minus 1. Where IS is the saturation current. Saturation current is a result of the design, the physical design dimensions, and the doping profile of the semiconductor. VBE is, of course, 0.6 to 0.7 volts. Thermal voltage, VT, if it's given, then you simply use that value. If it's not given, you can assume 5.8 volts. Either the thermal voltage would be given or the temperature would be given, and you'd have to calculate for your own. Okay. Right. From the same equation, we can derive an expression for the base current. IB, we know the relationship between IC and IB, right? The ratio of IC to IB is beta. So IC is equal to beta times IB. We can reverse that, and IB is equal to IC over beta. And so I can take this entire expression and write divided by beta, and I would get IB. E is to VBE VT minus 1. I would just as sooner get rid of the 1, just, but it's part of the equation. So typically when I do an approximation, if I want a quick answer, I would ignore that 1. Just E raised to VBE over VT. This beta, there's also something known as reverse beta, BR. So to make a distinction, we can label this as beta F. So the current gain in the forward mode of operation, okay, the forward transport model. So beta F is forward current gain. Okay. Reverse characteristics. Now we simply look at reverse bias of the collector base junction, where VBE is now 0 because we're not applying any voltage, and we find the reverse current. The total current in the device would be the forward and the reverse total together. Okay. So this reverse current, VBE, is equal to 0 volts. Okay. And now instead of IC, we have IE. Okay. Reverse current is flowing in the opposite direction, IR, and IR is going in the opposite direction to IE. So we can write out IE is equal to minus IR. We can express IE similar to the previous slide. So IE is IS into E raised to VBC over VT minus 1. Okay. And then from this, we can also write an expression for IB similar to how we did for C. Right. So from these two, we can write the complete transport model. Now these equations, I was going to say you have to memorize these equations, but they're in the book. Even I don't have them memorized. But again, it's the forward current based on the diode equation, and then you have the reverse current based again on the diode equation. If you want the complete transport model, meaning both currents flowing because of majority and minority carriers, you simply take both, add them together. Okay. So IC can be written as IS times E raised to VBE over VT minus 1. And then, oh, sorry, not we actually combine both of them together. So it'd be e raised to VBC over VT. Subtracted because it's flowing in the opposite direction. And then we have to subtract, let's see, IS or beta R into E raised to VBC over VT minus 1, where beta R is the reverse or current gain in reverse mode of operation. Okay. There is a, let's see, let's finish writing this. IE equals IS times E raised to VBE over VT minus E raised to VBC over VT plus IS over beta R and E raised to VBE over VT minus 1. And IP is forward current, again, IS over beta F, E raised to VBE or VT minus 1. And beta reverse, E raised to VBC over VT minus 1. Again, you don't have to write this down. I'm just using this right now for information purposes, but it'll be part of the assigned reading in the textbook. Okay. Yes. Will we not use it or will we use it? Will we use it? Yes, a little bit. There's one or two I need to review. I need to review it, but I think there's a couple of problems with the transport model. Yeah. So we can look at an example next on how we can use the transport model to solve for a circuit. Okay. So here's a circuit. We are applying VCC of plus 5 volts, VBB of 0.5 volts, or sorry, 0.75 volts. We have the terminal voltages, we have the terminal currents, and we are asked to find the 3 terminal currents, IC, IB, and IE. Okay. We are given, let's see, IC, IB, and IE. And then we are given the forward beta F as 50, beta reverse as 1, saturation current IS is given as 10 raised to minus 16. And then, of course, the thermal voltage is not given, but you can assume. For simplicity's sake, let's assume 25 millivolts instead of 25.8, right? So with the transport model, without going into the other kinds of analysis, we have the equations. It's simple plug and solve, but we need to figure out what our voltages are. We need to figure out VBC, we need to figure out VBE. Okay. So if you're applying VBB as 0.75, sorry, VBB as 0.75, then in this circuit, what is VBE? 0.75. That's it. That's the answer. There's no other resistor to cause a voltage drop. We are simply applying that voltage across the base and the emitter. So VBE is 0.7, not 0.7, 0.75 volts. Or VBE is equal to VBP is equal to 0.75 volts. And the only thing that remains is to find VBC. So what is the base to collector voltage, VBC? Anyone? Simply measuring from the base to the collector. So collector and emitter is 5 volts. We have 0.75 volts in the base and the emitter, meaning we simply subtract and we get minus 4.25 volts. The solution for this is simply plug these. So now we calculated VBC and VBE. We take those values. We are given beta R, we are given beta F. Plug into those equations and solve, and we should obtain these three values. IC is 1.071 milliamps. IB is 21.4 microamps. And IE, sorry, this looks more like a Z than an I. IB and IE, 0.09 milliamps. Okay. The transport model remains the same, or not same, but similar to a PNP. In the PNP transistor, everything is flipped. Holes are exchanged with electrons, electrons with holes. Biasing voltages are flipped. Sources are flipped. Everything is flipped. Everything else remains exactly the same as an NPN. So it is same as an NPN BJT. Electrons and holes are switched. Okay, electrons and holes are switched. Let's see, 10 minutes left, but I want to. Okay. Right. You all remember electron and hole mobility. Not the values, but just the concept. Right. Electron mobility is about 3 times as much as hole mobility. And so I don't know if I brought that point up when we were doing p-n junction diodes, but what do you think of the performance of an NPN transistor versus a PNP transistor? Okay, one at a time. Go ahead. PNP would be slightly worse. What do you think? Okay, anyone else? Well, worse in terms of speed. The answer is yes. The performance is slightly, well, I wouldn't say worse in that sense, but the speed of these devices, speed and the performance of PNP devices compared to an NPN device would be lower. The reason for that is holes are localized in the structure, whereas electrons are free to move around anywhere. So the mobility for electrons is higher versus holes. Okay. So when we say and compare these two devices, we are saying that the dimensions of these devices, the design of the device is exactly the same. The doping profile is also exactly the same. That's when we can compare. But when modern advances, there are PNP and NPN devices that have the exact same performance because we design them a little bit differently. Design them and dope them a little bit differently. Okay. Anyway, equivalent circuit representation. We can describe the output. Did you have a question? Question being asked is, when we talk about speed, how are we measuring the time? Are we measuring in terms of like nanoseconds or microseconds? The answer is depends on the application. But yes. If it's just one transistor, I guess it doesn't matter, right? If it's nanoseconds, it doesn't matter. I mean, I press a button and the light turns on. Humans are, we can't distinguish between any of those, right? But when it's billions of transistors, then it makes a difference. Yeah. Okay. Equivalent circuit representation. The output, similar to an FET, the output side is modeled as a dependent current source. So you see the dependent current source modeled as a diamond with an arrow pointing down. So the output, which is the collector current, is modeled as a dependent current source. And we will see this later on in this chapter also, right? IC is beta IB. If IB changes, IC changes. IB increases, IC increases. IB decreases, IC decreases. Hence, IC, the output current, is dependent on the input current IB. And that's what is being shown here. Okay. The total current flowing on the output side is the forward current minus the reverse current. This is for the NPN transistor. This is the NPN transistor, and this is the PNP transistor. But in both cases, again, the output current is modeled as a dependent current source. And the dependency is that it is controlled from the input side by either the voltage VBE or the current IB. Okay, controlled either with VBE or IB. And in later, we'll look at the pi model and the hybrid pi model, and we'll see that we can control either with VBE or with IB. Okay. A few more minutes left. Let's talk about operating modes. So we have the collector-based junction and we have the emitter-based junction. We spoke about operation of the device where the emitter-based junction is forward bias and the collector-based junction is reverse bias. This is known as the forward active mode of operation. In this mode, we can use the transistor as an amplifier, which is lab 8. In lab 8, we are going to design an amplifier using a BJT, and we are going to create or recreate and make sure that our design works in the lab. Lab 8 is by far the shortest lab for the entire quarter. Or it could be the longest one. Because if you design it correctly, all you got to do is you come in, build your circuit, apply input, you're done. 10 minutes tops. However, if it doesn't work, then you're going to be there for like hours trying to make it work. All right. So forward active is an amplifier. If you reverse bias the emitter base junction and you reverse bias the collector base junction, nothing happens. If you reverse bias the emitter base junction, the majority of the action, not majority, the action begins in the emitter. So the emitter junction itself is reverse biased. The electrons are not going anywhere. Nothing's happening. Everything's cut off. Hence, cut off mode of operation. Okay. And if you forward bias both junctions, well, you have a plethora of charge carriers crossing over everywhere. And then you have what is known as saturation. Okay. So in terms of switch, if it's cut off, we can say this is open. And if it's saturated, we say it is closed. And you take both modes together, we can use them as a switch. And it forms the basis for digital logic circuits. TTL topology. TTL is transistor logic. You can create digital circuits using BJTs. Okay. How about reverse active? When emitter base is reverse bias and collector base is forward bias. What use is there for reverse active? For those of you who finished lab 7, did you encounter the reverse active mode? Maybe, maybe not. If you know the terminals of your transistor and you just hook up the circuit correctly, then it's fine. But it's still worthwhile knowing what would cause a reverse active mode. If your emitter base junction is reverse bias, nothing's happening. Electrons are not going anywhere. Right? The collector base junction is forward bias. Maybe some current flows through that forward bias junction. Other than that, nothing is happening. There's no amplification, nothing happens. There are equations and stuff that but describes stuff happening in reverse active mode of operation. But for all intents and purposes, we never use that mode. But for electrical engineers, it still behooves us to know what the reverse active mode is. If we encounter it, then we should be able to pinpoint and understand that this is reverse active mode. So then we change our approach. Okay. So again, reverse active mode is not used, but it still behooves us to be familiar with what that mode is. Okay. All right. The bell rings. And so I will say we'll end class here today. And well, it's actually the perfect segue right there. We'll pick up with biasing modes from onward from Friday.